Hello, my dear students. Today topic for the discussion is the operating performance characteristic of synchronous machine. Though this topic we have studied in previous semester, still this is very important in the reference of the current semester as well as good point of view, due to which I am going to again repeat and explain this topic. Okay. The effect of the changes in mechanical or soft load on a nature current. We are talking about synchronous machine. The effect of the changes in mechanical or soft load on armature current, power angle and power factor can be seen from the figure diagram as shown in figure below. As the applied stator voltage, frequency and field excitations are assumed constant. The performance characteristic is the variation of the change in the load, mechanical or soft load, okay, due to network it's disconnected. Now we have studied in previous semester about the power, mechanical power and electrical power. Electrical power out in case of generator, and mechanical power, there will be mechanical power input. In case of motor, there will be output will be mechanical and the input will be electrical. Where E stand for electrical and M stand for the mechanical. Okay. In case of motor, Pm is the net mechanical power input to the machine. Whatever we have input to the generator, after deducting the iron loss and windage loss and friction loss, after reducing all the losses, from the input mechanical power, that will be finally we will get the Pm. That will be, this Pm is finally available to the shaft of the motor, generator, and that is known as denominated by the Pm. But in case of motoring machine, Pm is Pm out, means that power that will be available finally at the shaft of the motor. Gross mechanical power output of the machine. The net mechanical power output will be obtained by deducting the iron loss and windage loss, windage and friction loss. Means net means, what does it mean? Net power is the net mechanical power which will be obtained by deducting or reducing the iron loss and windage loss from the gross mechanical power. Is that clear? Now power angle characteristics. The machine is assumed to be connected to infinite bus bars of voltage Vt. It is easily observed from the phasor diagram that in generating mode, the excitation EMF EF leads Vt by angle delta, and while it lags Vt in motoring mode. What does it mean? When generator or synchronous machine will be operated in motoring mode, then this EF will lags terminal voltage or bus voltage or infinite bus voltage Vt by angle delta. What is delta? Delta is the angle between EF, excitation voltage, and the terminal voltage VT. These are the assumptions. Okay. Now, if the follows from the phasor triangle, it follows from phasor triangle OMP. Now we will look into triangle OMP, and only we will analyze how the variation of the active power P, voltage VT, and E sin delta. How when PE, either P or E sin delta will change, then how and what is the relation between VT, EF, and sin delta, right? This is the circuit diagram of the synchronous machine. Simply, this is the synchronous generator, and this is the synchronous motor. We can see here in generating mode, the current will be supplied, and this current will be received by the load, load end or load terminal. This is VT is the terminal voltage or load voltage. This EF is the excitation voltage of the generator, and XS is the synchronous reactance. Similarly, in case of motoring mode, this relation will be relation between voltage and excitation voltage will be simply EF will be equal to VT minus JIA XS. How you can apply the KVL in this circuit? This is the motoring mode. This means current will be consumed, electrical power will be supplied, current will be supplied to the motor, and this synchronous motor, and this is VT is the terminal voltage, and EF is the excitation voltage of the motor, XS is the synchronous reactance. If we will draw a phasor diagram of the synchronous machine, first this is the diagram for the lagging mode, and this is diagram for the leading. Because here current IA, armature current, is lagging by angle phi, and this EF is lead. This EF lead this reference or the terminal voltage VT by angle delta. If you will draw the phasor diagram, then this is IA, this is terminal voltage VT, and this EF is the net voltage or resultant voltage. This voltage will be equal to the voltage across XS, reactance across the synchronous reactance, and the terminal voltage VT. Right? You can see here, this is terminal voltage, and this is the voltage across the synchronous reactance IAXS, and this IAXS will be perpendicular. This is the reactive voltage, and hence it will be perpendicular, and 90 degree lead JIXS will lead 90 degree to the reference line or to the current IA, armature current. If IA is this one, then JIXS, simply IXS is the voltage across the reactance, and J, when J notation is multiplied to the reactance to any constant, then it's this magnitude or this vector rotate by 90 degree in leading mode or in clockwise direction, sorry, anti-clockwise direction, right? You can see this is the direction of IA, and when JIX will rotate 90 degree in anti-clockwise direction, and it will perpendicular to the IA, and this will meet at point P, and hence this VT, this EF is the resultant, will be equal to the sum of the voltage across the reaction synchronous reactance and the terminal voltage VT. This is the VT and this is the GIXS, means voltage across the synchronous reactance, and this will be the resultant. You can see here this angle delta, torque angle or power angle delta is the angle between VT, terminal voltage, and the excitation voltage of the synchronous generator. And where phi is, what is phi? Phi is the power factor angle. Simply, it will be simply voltage between terminal voltage and armature current. Whatever current flow from the generator and the terminal voltage or load voltage, right? Now, similarly, if we consider in lagging mode, here VT and EF excitation voltage is lagging by angle delta, right? In that case, this angle phi will be phi power factor angle will be greater than the angle delta, and the final vector phasor diagram will be like this. This is EF, and this EF will be equal to the, in case of motoring mode, EF is motoring mode. This is the supply voltage, and this will be the voltage available at the motor. This means supply voltage. This supply voltage will be equal to the voltage across the synchronous reactance and the excitation or the voltage across the motor. You can see in the diagram. This VT terminal voltage will be equal to the sum of the voltage across motor, that is EF, and the GIXS, voltage across the synchronous reactance. This is phasor diagram I have already explained in previous semester, and now we have to understand the main point in this lecture is that using, you have studied in trigonometry, you have formula, a theorem, like this side in a triangle, angle sine of any angle, ratio of the any sides in a triangle, sides with the sine of the angle will be equal in any two triangle, right? Similarly, this is the EF, and the angle of in front of this side angle will be, this angle will be, do you know what will be angle? What will be this angle? This angle will be simply 90 plus phi in case of this lagging mode. 90 plus, how? Because this is phi, this is 90 degree, and hence this angle, just I want to change the color of the video. This angle will be simply 90 minus phi, right? Just 90 minus phi, 90 minus phi. Sorry, 90 minus 5. This will be 99. Just a second. And okay, just it's not working. 90 minus 5. Right, and hence this angle will be 180 minus 90 minus 5, and it will be equal to the simply 90 plus 5. But in case this angle and this angle will be simply, sorry, OMP. This is OMP triangle, OMP, and point, and this angle will be simply 90 minus 5, right? Because this is 5, this is 90, and hence uh, this angle will be 90 minus 5. Hence it is taken simultaneously 90 plus minus 5. EF, this side divided by sine of its front angle, sine 90 plus 5 will be equal to simply IA excess upon sine del. This is IA and IA and IA excess means this branch side, and sine del delta is its front angle is delta and sine will be sine del. In any triangle, there is a theorem. Ratio of its sides and its front sine of its front angle will be equal to the ratio of the other sides and sine of its front angle. Though I forgot this theorem, the name of this theorem was D. Lambert or something else. You have studied in trigonometry and at 12th level. As per this theorem, this become this relation has come EF upon sine 90 plus minus 5 will be equal to the I axis sine del. From this, okay, from this relation we can determine, just a second, I want to delete it. Okay, from this relation, you can say IA cos phi. This IA sin 90 plus theta will be simply cos phi. IA cos phi will be simply EF into sin del by X. This relation has come. Okay, where phi is the power factor angle. Right now, IA cos phi. If we multiply with voltage, terminal voltage of the load with IA cos phi, this will be simply power, electrical power received or delivered to the load, right? VT IA cos phi, this will be equal to simply VT into EF X upon X sine del. Okay, from equation 8.41, and when we will multiply it by VT in both sides, then it will become some VT IA cos phi will equal to VT EF by X sine del. Okay, this VT IA cos phi, VI cos phi becomes active power E, TE, electrical power delivered from the synchronous generator, and it will be equal to VT EF by X sine del. You have to remember this formula very carefully, right? This is very important formula. Many numericals and many conceptual questions raised in GATE and ES on the basis of this formula. You have to remember it, and you have to understand it also. Now, okay, let's now, if you draw the phasor diagram or the wave form using this formula, EE equal to VT EF by X sine del, this means simply it's this power wave will be simply sinusoidal. Okay, sun delta angle of this delta from the stability point of view, it's vary from 0 to 90 degree. Okay, if its delta is positive, then it will be, work as generated in generating mode, and when delta will be negative, it will work like motor. You can understand from this waveform. Uh, if the delta is positive from 0 to 180 degrees, sorry, delta will vary from 0 to 180 degree, and from 0 degree it will be P will be simply 0 because sandal will be 0. When sandal will be 90 degree, this means uh, this will be sandal. Sun 90 means it will be 1, hence it will PE will be maximum, and that maximum value will be simply coefficient VT by XS. Similarly, when delta will be negative, it will direction of the power flow will be reversed. You can see here in generating mode power flow was positive, while in negative or motoring mode power flow will become negative. It's depend upon the power angle. A synchronous machine will work as a generator or the motor. It's depend upon the power angle. Be careful and note it down. If you will change the power angle or torque angle delta from positive to negative, then the mode of the synchronous machine will be changed. It will become from generating mode to motoring mode when it delta change from then positive to negative, right? You can see from this graph. You have to keep this graph in your mind. It is very useful. Now some special consideration you have to consider here. Uh, at constant load. What does it mean? At constant load means PE will be constant, and PE will be constant. This means PE will be constant. What does it mean? Simply EF sandal will be constant because PE equal to EF VT by XS sandal. Here VT is already assumed constant for the given synchronous machine. Synchronous reactance will be constant, and hence remaining two things EF and sun delta must be constant if you have considered the load is constant. Is it clear? I hope that this line is clear to you all. EF sandal, when EF sandal will be constant, this means load is constant, and hence EF sandal constant means PE excess upon VT will be constant. And similarly, VTI P will be constant means VTIA cos phi will be constant. From this we can conclude that IA cos phi must be constant, right? These things you have to understand. When in case of synchronous machine, when the load is constant, when there is a statement like constant load, this means EF and del will be constant. Similarly, we can say IA cos phi will be constant. IA cos phi means product of the current, armature current and power factor. Similarly, product of the EF and sandal. Not individual quantity will be constant like EF or sandal individually, or IA or cos phi individually. It will not be constant. But product of the EF sandal will be constant, and product of the IA cos phi will be constant if we have considered the constant load. Okay. Now this graph of the variation of the delta with respect to the EF, when delta will be changed, then this EF sandal, you can see here EF sandal, if this is delta, okay, this is delta, and this is EF, then sandal, EF sandal will be this one, right? And this is the armature current IA. It will be perpendicular to the JIA axis. JIA axis will be simply perpendicular to the armature current, and this is the terminal voltage VT, right? You if you this variation from the animated GIF video you can understand from this one, right? Uh, sorry. Yeah. Uh, are you able to see this GIF video of the variation phasor diagram? Phasor diagram of the P equal to EB sandal. You can see here this green line is voltage across the reactance JXI, right? And this red line is the simply armature current IA. And this black line, reference line, which is constant, is voltage. And this blue line is the E. You can see this E is constant. E sin del, value of the delta is the angle between the this V and E, blue line and black line, is delta is continuously vary, okay? But E sandal means this curve is remain constant throughout the movement. Locus, right? The locus of the E is the portion of the circle of the radius E, right? So locus means the moment of the points is known as the locus, and this moment of the E vector is the portion of the circle of this portion of this circle, right? Of radius E centered at the origin. Its center is origin of the complex plane, and locus of the I. This is I. You can see there I cos phi. I cos phi means cos phi angle between V and I. You can see here I cos phi is still constant. I cos phi is the locus of the I, also a circle of the radius E by X. Okay, this radius is E by X, centered on the imaginary axis at minus V by X. The power P versus the torque angle delta is also plotted, and this is a plot of the power versus torque angle delta. You can see here, as the torque angle delta increases, the power P is increases proportionally. Sinusoidally, this increase. This is depicted here from 0 degree to 90 degree. You can see when angle was 0, power was 0, but when its angle was 90 degree, it's maximum. And here you can see here constant, it will again decrease after the 90 degree. Is it clear? I hope that you can more visualize, you can more understand from this diagram about the variation of the power, plot or graph between the power P and the torque angle, and the variation of the E sandal and constant E sandal and constant I cos phi from this plot. Okay. Now you can say it is therefore observed that the constant load as the excitation EMF EF is varied by varying field current IF. EF varied by varying the field current IF. The power angle delta varies. If the EF will change, similarly, automatically power angle delta varies, so that the product of the EF sandal will be constant. Okay, you can see here the product. This is blue line is E and green line is the JXI. and this is Sandel. E Sandel. Okay, this E Sandel is remain constant throughout this locus. Similarly, I cos phi, this I and this is the locus of I cos phi is constant. Okay, this same line are stating here. The machine behavior is depicted by the phasor diagram. Machine behavior means it's working on leading or lagging. As ear varies, the tip of the phasor ear moves on a line parallel to the beat. Yeah, this diagram, this thing you can see here also. This diagram, this same thing has been represented or shown or explained in that animated or GIF video. You can see here, this is the VT and normal condition, the excitation is EF2, under excitation is EF3, and over excitation in case of this excitation voltage will be EF1. Right? You can see here, if we change the EF excitation voltage by varying the field current IR, excitation from over excited it will become normal, it again decreases, it will be under excited, but product of E Sandel is still constant. You can see here E Sandel. E Sandel means this perpendicular component will be E Sandel. It will be constant at whatever be the excitation voltage, either will be under excited or over excited, but its constant product of the E and Sandel will be constant, and it will be equal to PE excess by VT. Similarly, in case of I cos phi in submotoring mode, you can see motoring mode under excited, E normal excited, and this is the over excitation. E Sandel will be constant in case of motoring mode also. Right? We have to remember this thing. Generating machine, in case of generating machine supplies a lagging power factor current when overexcited. Means when generator will be overexcited, it will be work like an inductor in lagging mode, and hence lagging power will be supplied. But when machine supplies a leading power factor current when under excited. In case of under excitation of the generator, it will be work in leading mode. Means it will work like a condenser capacitor. Similarly, motoring mode, you can call the weaker. In case of motoring mode, over excitation it will be leading. It will work in leading mode, and under excitation it will work in lagging mode. In case of motoring mode of the synchronous machine, right? Okay, this is not this is the beaker. You can see here, beaker overexcitation, beaker synchronous machine constant load, overexcitation, lagging, and under excitation leading. If it is generator, it will be leading. If it will be motor, it will be lagging. You have to remember this thing, very important. Many questions has come in GATE as well as other examinations like UPPCL. You have to remember here these lines and these lines, right? Observation. The most important conclusion or observation you can say here, in a synchronous machine, the real electrical power exchange with the bus bar is controlled by mechanical shock power irrespective of the excitation. The excitation, on the other hand, governs only the power sector of the machine without affecting the real power flow. Okay. without changing the real power flow of the synchronous machine. The you can change, you can govern uh, the excitation. Uh, excitation, on the other hand, govern only the power factor of the machine. By varying the power factor, you can govern or control the factor of the machine without changing the real power, because in case of constant load, X and del will be constant. Okay. However, it is desired to adjust the machine power factor, its excitation should be varied well within the limit imposed by equation 8.46. What was that? Equation 8.46. This minimum excitation must be there. To sustain or to retain this minimum excitation voltage, we govern the excitation voltage sine torque angle delta. Okay, the minimum permissible excitation voltage is corresponding to the stability limit. To sustain the stability of the synchronous generator or generator, we have to there is limit delta must be within 90 degree, maximum up to 90 degree. It's vary from maximum up to 90 degree. Okay, and this is simple graph, you can understand it. Field excitation under unity power factor, it will be constant. While lagging power factor, it's more excitation current will be required. In case of leading power factor, it's required less armature current. Now you have to, if condenser, this synchronous machine act as a condenser capacitor, its graph will be like this. I armature current will lead to the terminal voltage, and armature current will lag if it will act as an inductor, right? I will be simply, armature current will be simply EF minus VT by XS. EF will be greater if it overexcited. EF will be less than VT if it is underexcited, and its armature current will be decided by this equation. I will be simply EF, the voltage difference between the excitation voltage and terminal voltage, divided by the synchronous reactance. Thus, the synchronous motor at no load behaves as a variable condenser or inductor by simply varying its excitation. This means synchronous motor maybe act as a condenser as well as the synchronous motor. It will work as a capacitor as well as the inductor by changing or governing its excitation. You can see from this equation and the previous graph. And hence, there is a dual purpose of the synchronous motor. It's drive the mechanical load as well as it's improve the power factor of the load. If there is a problem and there is a lagging load, to counterbalance it, there will be need of the leading load. Then there is a synchronous motor in overexcited synchronous motor, underexcited synchronous motor, which is connected there, due to which it's counter the problems. Okay, hence this synchronous motor work as a dual purpose. Okay, I hope that each and everything of this lecture is clear to you all. Still, if there is any doubts or question in your mind, you can ask in group, WhatsApp group, or through mail. Okay, thank you so much.